It is so-called least squares problem. Okay, well, minimizing so-called convex, we'll come back to this in a minute, convex quadratic function over no constraints. And this is a very nice nonlinear optimization. In general, we say a least square problem is the minimization of the following vectors L2 norm. First of all, what is L2 norm? So given a vector x, want to measure its size, one standard way is L2 norm is the square root of the individual entries squared, summing over all the entries. We often don't like the square root thing. We take the square of the L2 norm. So square of the L2 norm is simply the sum of the xi squared over I. It's a very standard way to measure the length of a vector. And we would like to, in least square, minimize the L2 norm square the length of the vector AB minus C, where B is our variable. A is a known matrix, C is a known vector. Say if A is n by m, then B is m by 1, a column vector, and C is n by 1, another column vector. In the particular case we just saw, we can also write this problem, minimizing this expression, in this standard form. It looks a little weird, but you soon see it's all right. The matrix is 1, 1, 0, 1, 0, 1. The variable vector we have is b1, ba, bb, and the constant vector term we have is r1a minus r bar on r1b minus r bar. This is our a, this is our b vector, this is our c vector, just to conform to the standard expression that we want to minimize in the least squares problem. You can easily check minimizing this is this L2 norm squared is the same as minimizing this expression. Okay, for example, this is just saying b1 plus ba minus r1a plus r bar, and that's exactly this term, right? And then you can write out the other term, and then just by definition of the square of the L2 norm, you see we're recovering exactly the same objective function. So we are in the baseline predictor problem solving a least square problem. So the question is, how do we solve a least square problem in general? Okay. Well, in general, we want to say we want to minimize AB minus C's L2 norm squared, which can also be written out as AB minus C transpose times AB minus C. Just it multiplying itself, inner producting with itself. You can write this out if you're not comfortable with the matrix notation in scalar format. You can write out a little 2 by 2 matrix A, 1, 2, 3, 4, and a little vector b1, b2 minus a little vector c1, c2, and then you can see that the derivation coming up is no mystery. But to save time, let's use the shorthand matrix notation. It's almost similar to our scalar operation. Okay, this will be AB transpose times AB minus AB transpose C minus another AB transpose C and plus C transpose C. And this can in turn be written simply as by transpose rule B transpose AB minus 2 times B transpose C plus C transpose C. Okay. Now we say if we want to minimize this expression over the variable which is B for a given A matrix and C vector, you can just take derivative of this with respect to B. Just like taking derivative with respect to, say, x of a quadratic scalar function, say, x squared plus 2x minus 3. We take the derivative, we get 2x plus 2. Right. Here we can take derivative with respect to b, and we get the following. 2, because there are two b's here, times a transpose a times b, minus 2, because of this 2, take derivative with respect to b, we get a transpose c. All right, now we set it to be 0, set this to be 0. Now, why is setting the derivative to be 0 going to give us the right answer? We'll come back to that in a minute. It sounds intuitive, but we will soon see that there's some complexity argument behind that. But right now, they just set it to 0. And that means a transpose a times b equals a transpose c. This is the solution to our least square problem. If you want to solve this problem by picking the right b, well, the right b is the answer to this equation. What kind of equation is it for b? It is a linear equation. A transpose a is just another matrix times b equals another vector, which is a transpose c. So as long as we can solve this linear system of equation, we get the right answer, b star, that solves the least square problem. This is a general theme that minimizing a convex quadratic function boils down to solving linear equation, because you take derivative once, you get quadratic back down to linear equation. All right. So everything that we're talking about eventually now boils down to a simple least square solution. So let's take a look at this one more time. We say our baseline predictor is the lazy R bar plus bias term for the users and the movies. Then you look at the difference between the actual R and this R hat in the root mean square error sense, which means you're looking at the square of the L2 norm, and you're minimizing over BU/BI that function. It turns out picking the right BU/BI and therefore completing this baseline model boils down to solving this kind of problem. And this kind of problem is called least square in this format. And the least square solution is simply the solution to this linear equation. We'll go through a complete numerical example towards the end of the lecture, but this is a quick summary of where we have been. Okay. Now you may wonder, this is kind of complicated. Why don't I just pick BU/BI to be the average rating of across all movies for this user, and average rating across all users for this movie? Well, it turns out that's a reasonable guess, but it does not necessarily minimize our error metric, which is root mean square error. So all we're doing is to say, if you believe in this model, stick it into our error term, then you got to solve a least squares problem, which can be efficiently solved by solving linear equation, just like Google PageRank solving linear equation. But over there, it's a very different set of equations. And then once you get the optimal BU star, BI star, stick it back in here, you get your predictor that minimizes RMSE. It turns out that that's almost a good idea, except you need something else. You often encounter what's called overfitting. This is in the textbook and the advanced material. But basically it says that you can add so much parameters, all these BUs and BIs, and you can fine-tune them so well based on the ground truth in the training data that it loses flexibility and predictive power of the actual prediction. So we want to somehow minimize the impact of the parameters. We don't want to rely too much on hindsight perfection. We want to leave some room for foresight, because it's ultimately foresight that matters in predicting or recommending. One way to contain the weight of the parameter is to actually minimize the size, say L2 norm, of these BUs formed as a vector and these BIs formed as a vector. That's called the regularized least squares. If we use quadratic norm, then L2 norm is still a least squares. It's just a bigger least squares problem. But it does try to contain too much reliance on too refined parameters based on hindsight. Right. So after the baseline predictor, what we have is the following. We got the actual RUI. We got the baseline predictor R hat UI, which is the same as RUI minus R bar, the lazy average, plus the optimized BU and optimized BI based on solving the least squares. And we call this difference a shifted R called R2D UI, just a shorthand notation. In other words, we have removed in this R hat R2D UI the impact of the average and the impact of the per user bias and per movie bias. And we're going to take this as the starting point into our neighborhood predictor to look at similarities across movies and across users.